join you guys, even if only virtually. As Bobby knows, as all my friends know, the ICTP is one of my very, very favorite places on the planet. Um, and I love coming there as much as I can, just for personal reasons. I haven't been able to travel that much in the past couple of years, but I certainly hope to be able to make it there again in the future. Um, uh, I love Blackboard talks. I think, well, the whole purpose of these schools is to have Blackboard talks. Um, I'm going to try to recreate it as much as possible with the iPad talk, although the first part today is just a general motivation and overview, so I'll use slides for that. But apart from that, I'll be writing on my iPad here. I know it's difficult, but if there's some way of doing it, Bobby or whoever else is out there, if the students have questions as I go, it would be great to be able to stop and take them.
Yeah, Nima, can you hear me? Can you hear this?
Yes, yeah.
Yeah,
Yes.
so, yeah, please, guys, if you want to ask questions, we just wait for the microphone to come to you, and then Nima can hear.
Absolutely, please do. We're in no rush. I have no very, very fixed agenda. There's some kind of set of things that I want to tell you about, but I would much rather go slowly and actually explain things than not. And given that it is more non-trivial to do it when this is over Zoom, I'll also stop, I don't know, every 20 minutes or so and just ask if there's questions accumulated to that point. And please do ask them. That's really the whole point of these schools. So I want to tell you about both some motivations for, as well as the background of, and finally some of the most recent developments. Some of which are not yet in the literature, on this general subject that many of us have been pursuing for the past 10 or 15 years, which is about trying to find a different way of formulating the basic laws of fundamental physics from a radically different starting point. So in this first, as I said, in this first part of the lecture, I want to give you some of the motivations for looking for this radically different kind of starting point. And also just some overview, very rough overview of what the kinds of ideas are that are involved. But one of the sort of basic points is that in thinking about completely ordinary physics, so not far away exotic places near the Planck scale, black hole singularity, beginning of the universe, just in physics right under our noses, what we thought we've understood fully for decades and decades now, there seems to be some real magic and some way of conceptualizing what very basic physical processes are involving scattering of elementary particles in particle physics and the generation of cosmological perturbations in cosmology. That there's some new way of conceptualizing what these things are, where the idea, the usually foundational ideas of particles moving in space-time, wave functions evolving in Hilbert space, are nowhere to be seen. And instead, different objects, structures, ideas, mathematical structures in combinatorics, algebra, and geometry instead come to the fore. And then from these different starting points, you can understand how the usual rules that we associate with particles moving in space-time and wave functions evolving in Hilbert space emerge. So that's the sort of origin of this title. This title would not have, I think, made even any sense 20 years ago. It would seem insane if you told, some experimentalists at the LHC that combinatorics would have anything at all to do with what they're doing. And it would seem similarly insane to a mathematician if you told them that these ideas would have anything to do with the physics. But that's one of the sort of fascinating things which has happened in this business is very basic physics, not super fancy schmancy partition functions of complicated theory X on difficult manifold Y, but basic physics about the interactions of elementary particles are related to very basic and deep new parts of mathematics in a way that's surprising to people on both sides. Okay, so that's what I want to tell you about. But let's start with the sort of reminder of what our foundational concepts are. I mean, the revolutions of the 20th century were space-time and quantum mechanics, and you all know that quantum field theory is that theoretical structure that tells us how to put these two rules together. Tells us how to describe worlds with which are quantum mechanical and also have Lorentz invariance. Of course, a particular quantum field theory, the standard models of particle physics and cosmology, describes everything we've seen from distances of 10 to the minus 17 centimeters, the short distance frontier at accelerators like the LHC, all the way up to the size of the observable universe around 10 to the 27 centimeters associated with cosmological observations. So this is certainly the most successful theoretical framework we've had in physics ever. But there's also the famous storm clouds that all of you at a string theory school know all about. We have our sort of famous thought experiments that if we take a magnifying glass and look at a small region of space, when we look, because of the uncertainty principle, we need more and more energy to probe tinier and tinier distances. And at some point, we put in so much energy to the region that we're looking at that it collapses into a black hole, and that makes it impossible to see what's going on, even in principle. So this is associated with the sort of quite famous fact that because of gravity and quantum mechanics, the notion of space-time is very likely approximate. We can't even in principle make sense of questions involving arbitrarily short distances and arbitrarily short times. Something that used to be emphasized more, I mean, it's still well known, but I think it's worth remembering, is another aspect of this problem is that the entire reductionist paradigm is ultimately wrong. And that's because when we collide particles at higher and higher energies, exactly what we just said happens. We make larger and larger black holes when the energies get far above the Planck scale. And so that means that high energies turns into long distances again. Instead of this idea that's true in condensed matter physics, it's true. It was true for centuries in what we thought of as fundamental physics, that the fundamental laws are given to us at arbitrarily short distances and high energies, and this appears to be wrong. That ultimately, very very high energies turns into longer distances again, and so the entire reductionist paradigm is basically wrong. Now. Something else that, as people who know about quantum gravity, you know, and but I want to say in somewhat more physical ways that than the more formal ways that these things are often described, because it gives a better idea, I think, of the kind of the nature of the problem and the sort of size of the effects that we're talking about. These issues about space-time breaking down appeared to be localized near the Planck scale. But there is, of course, a sense in which the problem is much, much deeper than that and is visible at all scales. And this has to do with the sort of famous fact that there's no local observables when you have quantum mechanics and gravity together. And this is because of one of the basic facts about quantum mechanics is that to speak of anything precisely, we have to, because it's probabilistic theory, of course, we have to do the experiment over and over again to get sharp results by averaging over many trials of the experiment. We only get a sharp result, and the limit is the number of trials of the experiment goes to infinity. That's what it means, that it's a probabilistic theory. Something that in undergraduate quantum mechanics courses we emphasize less is that we also have to do the experiment with, in principle, an infinitely large measuring apparatus. And that's because if the apparatus has a finite number of degrees of freedom n, Well, there's a probability of order e to the minus n that, due to its own internal quantum fluctuations, it'll screw up the measurement. So, for example, if you or I want to measure the g minus 2 of the electron or anything, but we want to measure it to the insane accuracy of 10 to the power of 10 to the 40. It's a super exponential number, 10 to the power of 10 to the 40 decimal places. We can't do it even in principle. And that's because you and I are made out of 10 to the 30 things, atoms. And so by the time we do the 10 to the 10, the 10 to the 10 to the 30th decimal place measurement, we may have fluctuated into a cloud of dust. That would make it very hard for us to measure the 10 to the 10 to the 31st decimal place. Or more mild things, we could have a quantum fluctuation in our brain, and instead of writing down 7 in the 10 to the 30th decimal place, we write down 2. So any finite system has an irreducible amount of uncertainty associated with what it can speak of precisely of order e to the minus n, where n is the number of things that it's made of. Now, it's clear why we don't emphasize this as much in quantum mechanics courses, because the first source of error from doing the experiment n times has an error that scales like 1 over square root of n, the statistical error. The second kind of error goes like e to the minus n, so it's practically much less important. But it is, of course, ultimately important for establishing this fact that there's no local observables in gravity. And that's because if I try to do an experiment in a fixed size room, as I make the apparatus bigger and bigger, it gets heavier and heavier. And so before I can make it infinitely big to make arbitrarily precise measurements, it'll collapse the whole room into a black hole. And that will also make it difficult for me to do the experiment many, many times. So in any fixed size region of space, there is an irreducible intrinsic error of order e to the minus the entropy of the black hole that would eat up the room. So e to the minus area of the room over g Newton, that would infect everything. Okay, so that's why there's no local observables in quantum gravity. Sometimes people say this in a more formal way that has to do with diffeomorphism invariance. It's strictly also true, but it's a much less useful statement because it doesn't tell you the kind of size of the mistake that you're making if you believe that there are local observables. The size of the mistake that you're making is always non-perturbatively small in g Newton. It's always e to the minus 1 over g Newton. At every order in perturbation theory, there are other problems, gravity isn't renormalizable, et cetera, but those are much more mild issues. This very fundamental fact that there's no local observables is an e to the minus 1 over g Newton effect. Nonetheless, it's a very important thing. It tells you that there's no sharply defined local observables when you have quantum mechanics and gravity. And famously, if you're a string theorist, you know this means that the observables you're allowed to talk about when you have quantum mechanics and gravity are boundary observables, things where you can make the measuring apparatuses arbitrarily big and separate them arbitrarily far apart to do the experiment over and over again. This is why string theory has always been a theory about asymptotic observables. It started off as a theory of the S matrix, so a theory of exactly what we're going to be talking about a lot in a moment, scattering particles from far away, having them go out far away. That's something that you can talk about when you have quantum mechanics and gravity, and of course, very famously for the past 30 years, the universe in the box of NT de Sitter space, when we can do exactly the same thing. In the context of ADS, we've gotten used to this idea that okay, so if the universe is the inside of a tin can of NT de Sitter space, then the boundary observables are just pinging things on the walls of the tin can and watching them waves crash into each other in the middle of the space and come back out. And since the observations start and end at infinity, it's reasonable to look for a theory that only lives on the walls of the tin can. That's the basic idea of a holography. And once you get into this holographic mindset, which is of course a huge deal to get into that holographic mindset, if you want to know what kind of theory should live on this boundary, well, this boundary is a reasonably normal place. It has space, it has time, it has a notion of locality, there's a metric. it's a normal place. The boundary of anti-de Sitter space is a normal place that we're used to. It's a normal space-time. And so there's a normal theory that lives on that normal boundary that ends up being the holographic theory. Okay, so of course this is theoretically spectacular. It's given rise to this kind of slogan that kind of quantum mechanics is king. The quantum mechanics on the boundary is king, and space and gravity and everything else kind of emerges from the non-trivial, strongly interacting quantum dynamics on the boundary. Okay. So this is the sort of basic issue. There's no local observables in gravity. And our reactions to this issue have been for decades now to talk about boundary observables like the S matrix and boundary correlators in anti-de Sitter space. And in this case, sort of culminating in this sort of picture that space and gravity and strings can emerge from quantum mechanics. So on the other hand, I think, so that's the big theoretical success. The massive theoretical, I wouldn't say failure, because there's no even credible pictures to start thinking about it very seriously as far as I'm concerned, is the fact that none of these things look anything like our actual universe. And our actual universe, of course, our actual universe is much, much closer to flat space. Okay, so we're going to spend quite a bit of time talking about flat space. The observations that we do in the world around us are much closer to scattering processes in flat space. Okay, they're very far from boundary correlators in anti-de Sitter space. Very, very far from that. But they're quite close to scattering processes in flat space. Nonetheless, our universe is also not flat space. Very, very importantly, also not flat space. All of the deepest aspects of our questions about nature are ultimately cosmological, and I want to I'm stressing this point because while we've gotten very used to the emergence of space out of more primitive ideas, at least in the ADS picture, the time that flows in the boundary is the same as the time that flows in the bulk. So we don't have to touch time. Time is left alone. And that's exactly the thing which is the hardest, biggest problem to deal with in a cosmology is time. Famously at the Big Bang, where does time is breaking down near the Big Bang? Where is time going to emerge from? And of course, the most striking experimental discovery of the last 30 years is the fact that we discovered that the universe is accelerating. And I don't want to spend a lot of time talking about this now, but this really opens up an enormous can of worms because of this sort of famous fact that in an accelerating universe, we have a finite cosmological horizon. When we have a finite cosmological horizon, a fundamental finiteness is thrust on us that we've never had to deal before with in physics. What we see in the universe now is what we're ever going to see because the regions further away are being accelerated away from us, so light from them can never make it to us, signals from them can never make it to us. And so not only do we somehow obviously have to understand the emergence of space and time when we talk about cosmology, but the fact that we have access ultimately to enormous but finite number of degrees of freedom means that the rules of quantum mechanics become ill-defined. This is not saying that I'm not saying quantum mechanics has to be modified in ordinary experiments in the lab or anything crazy like that. I believe that in any situation where quantum mechanics can make a correct statement, it will make the correct statement. But what I'm saying is that there's lots of indications that in trying to think about what it even means to apply quantum mechanics to an accelerating universe, that we might need to think of some extension of quantum mechanics. And that's because quantum mechanics itself in this setting does not tell us what to do. Because we cannot make infinitely big apparatuses because we only have access to a finite amount of stuff. Now, this is maybe here a point worth making. You might ask, what is this relevant for? Why do I care about these effects? You told me that the difficulties are of order e to the minus area over g Newton. In this context, the problems that we're talking about would be of order e to the minus 10 to the 120. So who cares about this? Why does anyone care about this? And the answer is, for every practical question about physics inside our universe, we do not care about this. But where we do care about it is exactly those deepest existential questions about why, for example, why the constants of nature turned out to be what they are. All the questions that involve things that are sort of uniform across the entire universe, and especially in the context of thinking about de Sitter space, all the confusions revolve around whether we can make sense of this infinite picture of the infinitely forever, eternally inflating de Sitter spaces and their cousins. And it's that infinity which gives rise to all of the all the mysteries. Because while these effects are of order e to the minus 10 to the 120 for experiments in our universe, there's competing effects that go like that go like the what you might think of as the volume of the full de Sitter space, which is actually infinite. And so once you start trying to come up, answer questions like, why did we get these constants or not those constants in the context of something like the landscape, where you imagine there's different regions of this slightly different vacua with positive and negative cosmological constant, but the positive ones accelerating and inflating in different ways. Now you have to compensate these e to the minus area G Newton effects with these even larger infinite strictly volumes, and that's where everything becomes extremely confusing. So this, I think, continues to be the sort of hardest problem that we have to deal with in fundamental physics. But I want to stress what makes it so hard is that we have to understand the emergence of time, and also somehow perhaps think about extensions of quantum mechanics. It doesn't look like standard quantum mechanics is equipped to tell us how to deal with these issues. All right, maybe I can actually stop there. This was just so far just a little sermon about the basic challenges of fundamental physics today from my somewhat idiosyncratic viewpoint. There may not be any questions since I haven't said very much of substance, but maybe you can stop here to see if there's any questions. Nope. Going once?
Yeah, Nima, I actually have a question.
Yes.
Which is about the last point, the e to the minus 120.
Yes.
But so I normally think of de Sitter space as a metastable state in like something like an asymptotically flat space-time. So how does that fit in?
Yeah, that fits in beautifully, of course. I mean, this e to the minus area over G Newton is you can think of as the inverse of the Poincare recurrence time in de Sitter and so on. And the fact that in so many constructions, in fact, all the concrete constructions that we know of, although recently people are attempting to take the idea that eternal de Sitter space might make sense seriously, but I think anyway, if that kind of idea makes sense, it involves another change of rules like ensemble averaging and other things. And I think even the proponents of that idea are not sure it'll actually make physical sense. But if we come back to things where we understand, at least to some extent, how de Sitter is embedded in string theory in the landscape, of course, the whole point is in every such example that we know, the tunneling time out of the metastable de Sitter space is always faster than this Poincare recurrence time. It's always faster than this e to the minus what you'd get from a tunneling rate that goes like e to the minus area over G Newton. So that's good, but it just kicks it kicks the problem down the road to figuring out how to make sense of observables after you've tunneled out of the de Sitter. You might tunnel into another de Sitter. You might tunnel into a big crunch. None of those things help. you might tunnel into an asymptotically flat space region, and that was where things were left, back in 2000, mid 2000s, 2008, 2009. People tried to see whether there was some kind of boundary observables that you could associate with possible observers that could exist in some flat space regions that you tunnel out into. Um, um, but anyways, far from obvious, A, that makes sense, and B, why we would give a rat's ass about those observations. You see, in these other cases, like scattering amplitudes and ADS boundary correlators, I mean, you can say when we do experiments at the LHC, we're not sending particles from minus infinity and seeing them go back out to plus infinity. So we're also not doing a precise boundary experiment, and it's true, but we're doing something that approximates a precise boundary observable. That's not if what we're supposed to do is abandon talking about observables in the de Sitter and only talk about observables in flat space regions that we tunnel out into, then there's no simple relationship between the approximate observations we would make in our de Sitter and the potentially exact observations this other imagined observer in this flat space region would make. So it's not at all clear why we would give a rat's ass about what those observables are. So that's why it's so confusing, and that's why I and many other people think, probably you think, that this is probably the hardest unsolved problem in our field, and which at least I feel we're still very far from getting a handle on how to proceed. But I have to say, it's exactly these kind of questions that have motivated me for the past 15 years to be working on the main substance of the lectures that I'll now be telling you about. Because it's clear whatever we're doing, we have to really fundamentally reconceptualize space-time and quantum mechanics. And that's such a humongous thing that if it's really true, it's such a humongous thing that it has to have implications everywhere, even in physics that we thought we understood for a long time. And that's what I want to move on to describing. Any other questions? Okay. Now, what I now want to talk about is, so all of this is very highfalutin, almost philosophical, but just a tiny bit of content about why, as I said, we should find some way to reconceptualize what space-time and quantum mechanics are really about. But there's another indication for this much closer to home, okay, much closer to home, in thinking about scattering amplitudes. Now, particle scattering, elementary particle scattering is, of course, the most basic physical process in nature. A huge fraction of things we see in nature are just the consequence of the particles banging into each other over and over and over again. So there's a very good reason of course, they're experimentally important objects. This is the obligatory picture of the LHC whenever you talk about scattering amplitudes. Although I want to stress that the process that we're talking about are not just esoteric things that happen at colliders. They happen all the time in the world when you look outside the window. The actual world that has 4 dimensions and, the actual world, the world outside the window, has elementary particles colliding in just the way that we'll be talking about over and over again. It's just that at places like the LHC, we care a lot about measuring them in detail. But the processes are the most basic physical processes in the nature. And of course, we've also understood for a long time how to compute these. This is textbook quantum field theory. And Feynman taught us how to think about them in terms of the sum over histories pictures that give us Feynman diagrams. Okay? So just to emphasize this point, what Feynman diagrams are about, the reason Feynman is justifiably famous is that he managed to present the results in a way that manifested as much as possible both compatibility with the symmetries of space-time as well as quantum mechanics. Before Feynman, that was the problem. You could quantum mechanics made time a preferred direction, Of course, you could try to describe relativistic theories in that language, but if you did it in the standard sort of Schrodinger equation, solving a Schrodinger equation way, it would it would break manifest the Lorentz invariance. So that's what Feynman did. That's so important, is figure out how to conceptualize this in a way where both the rules of quantum mechanics and space-time were as much manifest as much as possible. But it's also exactly this picture that leads to what you would naively think of as an explosion of complexity and what the answer looks like as soon as you get away from the very, very simplest processes. Okay, so here's an example of just some representative diagrams for 2 gluons in and 4 gluons out. This is a process that happens, millions of times a second at the LHC, and it just looks complicated, right? Now, there's no reason the answer should be simple a priori, and certainly Feynman's picture would naively make you think the answer should get more and more complicated as the number of particles is increased. And part of the chauvinism of fundamental physics is to declare as interesting those questions that have simple answers, and to declare as engineering those questions that don't have simple answers. So this really looks like an engineering question. However, physics also has a great way of rewarding morally good behavior. And so people just needed to do this computation. Of course, if you do it flat out, you get like 100 pages of algebra that look like this using Feynman diagrams. But Park and Taylor discovered in the late 80s that, in fact, for some helicity configurations of the gluons, the final answer had this ridiculously simple one-term form. So those hundreds of pages of algebra collapse into a single term, this famous Park-Taylor formula. I won't define what these brackets mean here, but the magnitude of these things are the dot products of the corresponding momenta. All right, so this is shocking. This should be shocking, and when it was discovered, people were impressed, although it was not at the time understood to be the tip of a huge iceberg. I think a lot of people thought that it was kind of an accident, or maybe related to some very special features of Yang-Mills theory, when you're close to when most of the gluons have positive helicity, or most of them have negative helicity, you're very close to the self-dual limit of the theory, which is known to be integrable. So maybe it was related to that. So people, I think, did not pay it as much attention as they should have, even though it was obviously a very impressive result. Today, we know it's a tip of a gigantic iceberg. And that one lesson that we can already take away from this, that ends up being verified over and over again in the development since, is that our standard picture for thinking about these processes, whose entire purpose in life is to manifest the rules of space-time and quantum mechanics, is correct, is the most successful framework we've ever had for calculations in theoretical physics, et cetera, et cetera. We can bow down before it all we want. But it's also clearly hiding something. It makes us think the answer should be hundreds of pages of algebra, even when it's a single term. And so that's an invitation to say, could there be another way of thinking about things, which kind of makes it obvious that the answer is simple to begin with. Now, but whatever this other way of thinking about things is, clearly it cannot have the rules of space-time and quantum mechanics as the stars of the show. You make them the stars of the show, clearly you're going to get led back to Feynman diagrams. Okay, so whatever this new picture is, if it exists, it has to be one where space-time and quantum mechanics take a back seat, and some other ideas have to come to the fore instead. All right, now what I hope you see is that we now have 2 indications that we should reconceptualize things in some radical way. One of them is this very highfalutin one to do with the breakdown of space-time at the Planck scale and the difficulties with quantum mechanics and de Sitter space, all this fancy schmancy stuff. And then another one, it's super practical, that, look, if you think space-time and quantum mechanics is the most important things there are, you think the answer is hundreds of pages of algebra when it's a single term. So there has to be another way of thinking about things that makes this other feature obvious, right? I believe these two things support each other. I think these two things are related to each other. Um, Even though, of course, the first set of questions are fundamentally gravitational, you might think if you want to attack the first set of questions, you should spend all your time thinking about black holes or the singularities of the Big Bang or how to make sense of de Sitter space. Those are the most obvious ways of attacking the questions. They're the direct way of attacking the questions. But again, as I said, when there's huge conceptual shifts of this sort that have to happen, they often have echoes all everywhere, not just in the places that originally led you to suspect there had to be a big conceptual shift. And the analogy that I like very much, I've made in every sort of summer school lecture or pedagogical lecture I've ever given on this subject, is that this sort of transition that we're thinking we need to make now and moving beyond space-time, perhaps extending quantum mechanics, is humongous. And is, I think, only comparable to the transition we have to make in going from classical to quantum, where there too we have to lose this fundamental idea of determinism. That's so shocking. If you're a classical physicist, it seems so shocking that if someone came and told you from the future that you have to learn to give up determinism, you would think it's a completely insane thing because determinism is totally hardwired into Newton's laws. But then, as you explore the structure of classical mechanics, you see that, in fact, that there's other ways of thinking about Newton's laws that don't look so manifestly deterministic. It's the principle of least action, that the particle goes from A to B by sniffing out all the paths that it takes from A to B and choosing the one that minimizes the action. When you first learn this, it's very surprising. It looks not quite deterministic. It looks like the particle is thinking about where it's going to go in the future and then deciding to take some path that minimizes the action. And de Maupertuis and Euler and Lagrange and the people who ran into this were indeed kind of mystified by the fact that this other way of thinking about classical mechanics, it seemed so utterly philosophically different than Newton's laws actually existed. Today, we know why this other way of thinking about classical mechanics exists, because the world is not classical. The world is quantum mechanical. Determinism is not there, but the way we go from Newton to quantum mechanics is not to start from Newton's laws and randomly modifying it to making it by adding stochastic terms to make it non-deterministic. It is to start from a formulation of classical physics where determinism is actually not so important. In the principle of least action, determinism is not so important. And it can be smoothly deformed into the path integral picture for that reason. So this is an example where when you have some hints from the future that some extremely cherished principle has to disappear, that's some indication that you should learn to rotate and talk about what you have under your feet now in a qualitatively different way that does not make such heavy use of that concept, and that should show up. That should show up even in the old theory. Okay, so that's the point I'm trying to stress: is the coming of quantum mechanics was presaged, was hinted at already in classical mechanics by the existence of these alternate formalisms like the principle of least action. So I think we're in a very similar position today. If it's space-time and the rules of quantum mechanics that have to somehow be modified in a radical way, then we could be looking for a clue for that radical modification already in a way of talking about ordinary physics, away from the de Sitter space and black holes and so on, in a way that removes those concepts as primary. And there's another nice analogy with classical physics. Why did people find the Lagrangian picture useful? They found it useful because it made it way easier to do calculations. And that's another hint that's going on here. The sort of complexity of the standard way of thinking about things is another clue, a more practical clue for the need for a new way of thinking about things. And indeed, Lagrangians to do celestial mechanics in a way that he couldn't possibly imagine doing directly from Newton's laws, and that's I think another interesting aspect of this analogy. Okay, so saying this again, this sort of standard picture manifests the rules of space-time and quantum mechanics, but is somehow doing it at the expense of hiding some extraordinary new structures. And so that's what we're now going to, that's what we're going to focus on in these lectures. Sometimes, if you've heard, talks by most people who work on amplitudes, They will talk about how Feynman diagrams are complicated and we want to find other ways of getting the answer and so on. But you might be left with the impression that this is about finding tricks. It's about finding tricks to simplify the calculation. You'll find some cool variables or a change of variables or maybe some other way of writing the answer, discover, satisfy some differential equation. Lots of tricks to simplify the answer. That's not what we're doing. So I want to stress this point. I hate tricks. Tricks are my least favorite thing in the world. And so nothing in what we're talking about has to do with the tricks. Instead, we're really changing the nature of the question. In fact, we're not trying to find the answer. We're trying to find a different question. What we'll be trying to do in the rest of these lectures is finding a new question to which the amplitudes are the answer. Okay? So the conventional picture is that we throw in some particles from minus infinity, we measure them again to plus infinity. The data that labels this scattering process is just the energies and the momenta of the particles coming in and out. Maybe they're spins. Okay, that's it. Our experimentalist friend in Geneva scatters the particles in the morning, looks at the plots of what came out in the evening, and that's it. It's the theorist that says that, well, what explains what happened is that the particles went in, they banged into each other, then this happened, that happened, all these histories, we have to add them all up. This is a way of telling a story for producing the results of these boundary measurements. We're sort of integrating in to this blob the interior of the space-time, and of course the summing over all processes as a way to be compatible with quantum mechanics. So again, the conventional answer to this question is to fill the inside of this blob with local processes in space-time and unitary evolution in the Hilbert space. And what we're going to be doing is trying to find a different question. The point of this, where does this question live? This is going to be a big part of the lectures, is to sort of talk about where this structure lives. This structure is going to live directly in kinematic space. So, the data that specifies the scattering process is n momenta, P1, P2, P3, P4, and so on. Or maybe it's the dot products of the momenta. That's another way of labeling the data of the scattering process. But that is a space in which we will be living. Okay, so that's the space that of variables the amplitude actually depends on. And in that space, we're going to be looking for some new question that gives us the scattering amplitudes directly. Again, this interior of the space-time is not that space. The interior of the space-time involves an infinite amount of extra information, which is not there in the asymptotic momenta of the particles. Instead, we're going to be looking for a question directly in this kinematic space to which the amplitudes are the answer. And amongst other things, you see, unlike in standard holography where the boundary is a normal place. You see, here, if you ask, what is the kinematic space for boundary observables? What is the space, what's the data that labels boundary observables? It's points in space-time on the boundary. It has, again, a time, locality, metric. It's a normal place. Okay? Our space is not a normal space. Our space is just a space of n momenta. There's no metric on the space of n momenta. There's no time, nothing, right? So that already gives you an idea. Whatever we're doing has got to look somewhat more unfamiliar than other things that we've done in the past. In particular, there's no notion of time or time evolution or anything like that, at least obviously in this space. And so this already is some hints that if this kind of picture succeeds, it cannot be that sort of quantum mechanics is king and space emerges. It has to be something more abstract. It has to be some other ideas are primary. We're going to see what some of them look like. But the rules of both unitarity and locality are going to have to come out together. So it's not that one is more important than the other. They're both somehow they're both connected and come out of a different set of ideas. Now, in the way I've described it, it should be obvious that if there are these structures underlying space-time and quantum mechanics, they have to involve some new ideas. They have to involve new physical ideas and some new mathematical ideas. And if history is any guide, it's very likely that the ideas will be simple. The ideas that we're looking for should be simple, deep, but very likely more abstract than things that we've encountered up to this point. So I want to, in the rest of this lecture, I want to give you a flavor or a hint of what some of these ideas, what some of the physical and mathematical ideas look like, and then we'll, again, go through them, go through some examples in some detail in the rest of the lectures. Okay, so the main physical idea, there's a number of them, but the main one to get into your head early on has to do with this distinction between on-shell and off-shell. Okay, so you all know if we have a particle moving with some momentum p mu, then p squared is equal to m squared. So if we write that out, it's e squared minus p squared is equal to m squared, and so this defines some hyperboloid in energy momentum space. So satisfying this equation we say says that you're on this mass shell. But obviously, when we look at Feynman diagrams, it's crucial that for all the internal lines, they're not on shell. Otherwise, the amplitudes would all be infinity. The propagators all have these 1 over p squared minus m squareds. So these p's are off shell, inside. And of course, this is another way of saying also what's in every popular exposition, even of particle physics or quantum field theory, is the distinction between real and virtual particles. So the things on the outside of scattering processes are real particles. They propagate over infinite distances, large or asymptotically infinite distances. These are the particles that go click, click, click in the experimentalist detector. Whereas when we fill in the inside of this picture with all of these lines, all of the guys in the middle here are virtual particles. Okay, so they don't propagate they propagate over finite distances. What are they there for? They don't go click, click, click in anyone's detector. They're there as a very convenient fiction to manifest the rules of space-time and quantum mechanics. Okay, that's their purpose in life. No one sees them. Okay, so the physical idea is to eliminate virtual particles. Okay, so that's one of the physical ideas. Somehow we want to talk about this physics without ever mentioning the word virtual particle. Okay, we only want to deal with the on-shell data. We don't want to ever talk about virtual particles. Maybe here is a good place for me to pause because at this point we've talked about scattering amplitudes. We've talked about just trying to stay on shell. Never talked about talking about virtual particles. At this point, you might ask, why isn't what we're doing exactly what the S-matrix program in the 60s was about? If you have that question, park it, and I'll answer it at the end if people want to. If people want a detailed answer to that question. But the short statement is, in a sense, it's the precise opposite of the S-matrix program in the 60s, because in the 60s people thought that they could impose the conditions of locality, causality, and unitarity and somehow uniquely determine the answer. So their attitude was to take those principles as so fundamental that you only ever talk about them and nothing else. You just talk about causality, locality, unitarity, and somehow try to bootstrap and determine the answer from that. What we're trying to do is precisely the opposite. We try to find a question. We never make any mention of causality, locality, or unitarity, but we find some different abstract question that just gives us the answer. And then from staring at the answer, we can see that it also satisfies these standard rules. So the philosophy is precisely the opposite. And this has real sort of technical teeth, because in the end of the day, despite a decade of effort, the S-matrix program people could not actually figure out precisely what the rules of locality, especially causality, meant at the level of the sort of final answer of the amplitude. So it's a very interesting question to unpack more if people are interested in talking about it, but that's the short answer in the middle right now. But in fact, let me move to this question, at least in the simplest case where it does have an answer, which is that sometimes the rules of space-time and quantum mechanics are reflected in the amplitudes in a simple way. In other words, if you want to get rid of virtual particles, well, we know that we need them to get the right answer. So how are we gonna get those right answers if we're gonna refuse to talk about them? So let's think about this sort of simplest process, right? Where there's some massive resonance produced here in the middle in 2-to-2 scattering. The point that I want to make here is that these rules, locality and unitarity, are very simply encoded, at least in some at tree level, and then there's interesting statements to make at loop level, which we might get to in the later lectures. But let's just talk about at tree level. The rules are imprinted in a very simple way in the amplitude. Here you can see that the amplitude has a pole when this P1 plus P2 squared, that momentum is P1 plus P2. So this has a pole when P1 plus P2 squared minus M squared goes to 0. We would say when the virtual particle becomes real. And so the amplitude has a pole there. Now, this is already one feature of locality. The amplitude only has a pole that looks like that. It doesn't have a pole that looks like, for example, 1 over P1 plus P2 squared, P2 plus P3 squared minus M to the 4th. Okay? It doesn't have some crazy pole like that. It only has simple poles when some of the momenta of the particles go on shell. And that's precisely a reflection of the fact that in position space, the interactions are local in space. Okay? Local in space-time. Now, so locality shows up in what kind of singularities you're allowed to have. There's poles and poles in this special kind of location. Quantum mechanics tells us more. Unitarity tells us that we have to be able to interpret in the vicinity of the pole. We have to be able to interpret the residue on the pole as the product of an amplitude for producing this particle that's now real, the virtual particle that became real, the amplitude for producing it times the amplitude for it to a decay. Okay, so locality tells us where the singularities are, where the poles are, and unitarity tells us what happens near the singularities that it factorizes. Okay, and so again, this is just summarizing, at least at tree level, the rules of space-time and quantum mechanics are reflected cleanly in the amplitude. Localities is only simple poles when some sum of the subset of the momenta go on shell, and unitarity is a statement of factorization on poles. And so once you realize this, all of our highfalutin abstract discussion becomes very concrete very, very quickly. So when we say, oh, we want to find a different question in kinematic space, blah, 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 whose answer is the amplitude, what the hell could that possibly mean? Now there's a precise thing that it could mean. We want to find some different question. It's posed directly in the kinematic space of the scattering data. So this question, whatever it is going to be some mathematical question in the space of momenta, P1, in the space of all momenta, to which the amplitude is the answer. This question should not sneak in, should not be cheating to sneak in Feynman diagrams behind the scenes, anything like that. But this amplitude has to do something. In order to see if it's right or wrong, we can check if it's right or wrong. It has to have poles in the correct spot, and it has to give rise to factorization. Okay, that's what we have. That's what we have to do. So poles and factorization is the sharp thing that we are looking for. Now, if you think about it for a little while, you might think, well, gosh, how could I possibly get something that has poles in the right spot and which factorizes if it isn't Feynman diagrams, right? No, that's that gives you sort of an idea of the magnitude of the challenge. All you need to do is come up with some question that gives answers that have this feature of poles in the right spot and which factorizes, but which does not draw pictures of particles and and Feynman diagrams behind the scenes. Okay, so that's what we're trying to do. And just as an overview of what's been happening over the past 15 years or so, this is the emerging picture that in this kinematic space, in the space of n momenta, you begin with questions that are fundamentally combinatorial. Okay, now it should be, in hindsight, maybe not so surprising that combinatorics is at the bottom of all of this, because this kinematic space that we're talking about has almost nothing going on in it, as I've stressed a few times. It's not like the boundary of ADS, which is a normal space-time with a normal notion of time, locality, blah, blah, blah. This is a much more austere space, just n momenta. So if there's going to be any structure in the space, there's almost nothing for it to be other than basically combinatorial. Okay, so that's where it begins. So there's some combinatorial structure in this space. This combinatorial structure then determines some geometric regions in kinematic space. This is what we've come to call positive geometries, is that there are some interesting geometric regions in this kinematic space. This geometry in turn determines a function, or determines more precisely a differential form, but let's just loosely call it a function now, entirely by the condition that this function has singularities only on the boundaries of this geometry and nowhere else. And in turn, from this function, that gives us the amplitude. Okay, so and what's been interesting in this process is that everything here is, you can kind of see as being seamlessly connected. So the combinatorics determines the geometry, there's no choices. The geometry determines the form, there's no choices. So somehow there's really a completely locked path from this combinatorial structure in the kinematic space through to the actual functions that are the answers. We're going to see this in practice in detail in these lectures. The words that are associated with these ideas, the sort of first fully working example of it, still, in my view, the deepest one, the one that involves the most novel ideas, and still the most mysterious one, were the amplituhedra from back in 2013, back in 2017, and then more and more in recent years, and I'll speak about it quite a lot in these lectures, are the amplituhedra for gluon scattering at tree level, but at all loop level for gluon scattering in maximally supersymmetric Yang-Mills theory. The isosahedra were totally non-supersymmetric theories of colored scalars at tree level. In the past few years, this was first extended to all loop orders in this story of sometimes what we call surfaceology or surfacedra. And in doing that, another thing which followed was an extension of these ideas to now discovering to describing totally non-supersymmetric gluons of the real world, and also pions of the real world. No supersymmetry. Another thing which has happened in this period is the beginning of the extension of these ideas to describe cosmological correlators. And perhaps in my last lecture, we'll have some time talking about that. And again, what I'm personally most excited about with these ideas is that they really describe the real world, that world outside the window that I love so much, in a reasonable approximation. Of course, it's not all of the world, but it's a reasonable, it's not ridiculously far from the real world. It's in the right dimension. It has the right kind of particles, the right kind of interactions. And that all of this stuff is exposed hidden symmetries, new structures, and as I said in the beginning, real magic in physics right under our noses. All right, Bobby, I have 15 minutes left. Is that right?
Yeah, that's right.
Okay, terrific.
Yeah,
all right,
cool.
Great. So then I think let me give you, before we end today, since in a lot of the rest of the lectures, I will be talking about geometries, but I just referred to how we extract amplitudes from geometries. I want to spend some time talking about this here, just abstractly, just so you get an idea, because mostly we'll be focusing on drawing the pictures and the geometries in what comes next. Occasionally I'll stop to just show you how you get a canonical form or an amplitude out of it, but I want you to get this, this part of the idea kind of abstractly in simple examples first. So that's what we'll spend the next 15 minutes maybe talking about. The general idea is the following. I'm going to we'll only be needing for these lectures an especially simple version of this. Okay, so but I'm going to say it in a little bit of generality. We're going to be finding in this kinematic space, as I said, things that we call positive geometries. Now, what is a positive geometry? It's some region P in some space. Okay? It could be projective space, Rn, Euclidean space, many different kinds of space. But it's a region P with the property that has boundaries of all codimension. Okay. So just to give some examples, let me just do this here. Sorry. So, for instance, a triangle is a canonical form. Sorry, a triangle is a positive geometry. Okay. I mean, any polygon is a positive geometry. A cube is a positive geometry. Okay, because this has, of course, the interior is two-dimensional. It has edges that are one-dimensional, and it has vertices that are zero-dimensional. Okay, okay, so it has boundaries of all possible codimension. Notice that a circle is not a positive geometry. Okay, it has an interval, and it has a codimension one boundary, but it has no vertices. Okay, so this is not a positive geometry. This is a positive geometry. Okay. Why the word positive? We'll come back to this a little later. But positivity is somehow crucial in defining the interior of things. Okay. So let's say I want to describe. Let's say I want to describe the inside of this triangle. Okay. So this is the x and the y axis. So let's say this is the line x plus y equals 1. Okay, so then the interior of the triangle can be defined in two ways. One of them to say, well, it's all the points where x is bigger than 0, greater than or equal to 0, y is greater than or equal to 0, and 1 minus x minus y is greater than or equal to 0. Okay, so you see, these are positivity statements. These inequalities are positivity statements. Okay, so to define the interiors, you have to say that a bunch of linear forms, a bunch of linear functions are positive that define what the boundaries look like. So this is something you do in any number of dimensions. And if you cut out a space by saying there's a bunch of hyperplanes and each one has got to be positive, then that gives one definition of what we call what people call polytopes. Again, these are just generalizations, obvious generalizations of things that you know and love. Okay, so but you see the notion of positivity is crucial there to define what you mean by the interior. There's actually another way we could talk about exactly the same triangle, a dual way that we could talk about it. This way that we talked about it is sort of centered on what the edges are. There's another way it's centered on what the vertices are. Okay, so here there's a vertex 0, 0. This is the vertex 1, 0, and this is the vertex 0, 1. And so we can say that all the points in the interior are some points x and y that look like some weighted average of these guys. So it looks like some weight 1 for 0, 0, plus weight 2 for 1, 0, plus weight 3 for 0, 1. In fact, you might imagine that they're masses. It's like the center of mass. So in fact, if I just divide by W1 plus W2 plus W3, then different choices of W's will just give me a different center of mass inside this triangle. And so by scanning over all the possible W's, I'm also going to scan over the inside of this triangle. But again, crucially here, these weights are positive. Okay, these weights are positive, right? All right, so this in fact gives us, there are these two definitions of what polytopes are. Polytopes are all positive geometries, okay, but this is just sort of one good example. So polytopes are either defined as the sum of some weights of vertices divided by the sum of all the w's to make them weights, where the w's are positive, or they're defined by a collection of linear equations, like L1 dot V, sorry, let me just call it L1 dot L1 dot v greater than or equal, just call it x. L1 dot x, L2 dot x greater than or equal to 0, some number of equations, one for every facet, okay? Okay, so these are, if I write it this way, there'd be greater than or equal to maybe some constants on the right-hand side, okay? But in both cases, positivity is crucial, and that's where the positive and positive geometry comes from. This is sometimes called the vertex presentation or the convex hull presentation of a polytope. This is called the facet presentation of the polytope. And we'll actually be seeing examples of both of these. But anyway, that just to define what these regions are. Here I've drawn it a little bit more generally. It looks like in all these cases, obviously the shapes have sort of flat edges, right? They're cut out by linear equations. But there are more general positive geometries than the polytopes that don't just live in Rn or projective spaces. They live in Grassmannians and so on. And then the edges can be curvy. Okay, so that's why I'm drawing it as a more general curvy object. But for the lectures, for our lectures here, I'll only be talking about the flat cases. Okay. Okay, so that's what a positive geometry is. It's a real region that has boundaries of all codimension. It's a real geometry. We can talk about it, of course, abstractly mathematically. In our setting, this geometry is going to live in kinematic space. Okay, so we're going to see in the space of the momenta, these geometric structures emerge. Where will they come from? They will come from some essentially combinatorial ideas also in that space. We'll talk about that later. But imagine you get a shape like this. How do you get a function? How do you somehow get a function or an amplitude or something associated with the shape? And that's a second notion of a canonical form. Okay, so a canonical form is a unique differential form that has the interesting property that it has singularities on, and crucially only on, the boundaries of P. Now, what do I mean by singularities? Okay, this is another very important basic object. So we're going to talk about forms with singularities. And the key word here, the key concept is d-log forms. Now, what does this mean? So let's say I just have a single variable z. Then it is a form that near z equals 0 looks like dz over z. Okay? Now, what's special about dz over z? What's special about dz over z is that that's a singularity at z equals 0 that is completely coordinate independent. Okay? If you have this form that has a singularity that goes like dz over z around z equals 0, if you integrate this form around z equals 0, you get 2 pi I. Okay, so you can detect that it's really a singularity. It's not enough just to have a pole of some kind near z equals 0. For example, I could have dz over z squared, but this, if I integrate around, will give me 0. Okay, and of course that's because I can also redefine the form to just be using z equals minus 1 over w. This is equal to dw. Okay, but this one, the d-log forms are truly singular. Okay, there's no way of removing the singularity, and I can detect it invariantly by doing this little contour integral. Okay, so when we're saying that we're looking for a form, a canonical form, it's a d-log form. That means that its singularities are such that locally, wherever the singularities are, in some local coordinates, they look like the wedge product of d-log, 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 d-log. Okay, so they can only have d-log singularities. And the claim is that once you give me this positive geometry, there's a unique form that has the feature that it has singularities on the boundaries of this geometry, and not just the codimension 1 boundaries, codimension 1, codimension 2, all possible boundaries, and that the only singularities it has there and nowhere else. Okay, so those conditions are so strong that they often, and that's part of the definition of a positive geometry, completely determine this canonical form. So for example, for every polytope, there's a unique canonical form that goes along with it, with this sort of remarkable feature of only having D-log singularities on and only on the boundaries of the geometry. So let me give you some quick examples of this notion. So let's begin, for example, with the interval. Okay, so that's the very simplest thing that we could talk about. Let me actually just open this up here so I can also just do it in real time. So let's say I have an interval. This direction is x. Now, what can the canonical form be? So I want something that has singularities, D-log singularities that at x equals a and x equals b. So clearly, it should be like dx over x minus a and dx over x minus b. And if you thought about it, you might be tempted to just say it's that. Okay? But it can't be that, because this, with the plus sign, it certainly does have logarithmic singularities at a and at b, but this also has a logarithmic singularity at x equals infinity, right? At x equals infinity, this goes to 2 dx over x. So it also have a logarithmic singularity at infinity. That is illegal, right? The notion of a positive geometry is that the only singularities of this form should be on the boundaries on the boundaries of the geometry and nowhere else. Okay, so that's why the answer actually has to have a minus sign here. Okay, with the minus sign, now this thing goes away. The residue at infinity is a 0, and now this is a decent canonical form. Notice that there's a one choice to be made here. These canonical forms have an orientation. Okay, but that's a single overall sign. Apart from that, they're totally well defined. So let's look at the next example of a positive geometry, the interior of this triangle. Okay, so let's now go and illustrate how this guy works. So so we're going back to this example. Okay, so here clearly the boundaries are at 1 minus x minus y goes to 0, or x goes to 0 here, or y goes to 0 here. And so your first guess of the geometry, now it's a 2 form, because it's a 2-dimensional space. So maybe you say it's dx dy divided by, well, where the poles are. It certainly has to have singularities here at x equals 0, and at y equals 0, and at 1 minus x minus y equals 0. Okay? However, we're not done. So when I say it has to have singularities on and only on, and all possible boundaries, what I mean is the following. So obviously this form has a d-log singularity, let's say as x goes to 0. But then we should be able to take a residue of this form on that spot. So let's say I take a residue of this form on x equals 0. So that means I'm going to be localized here now. I'm going to be localized on this line. So if I take a residue of this form on x equals 0, well, you imagine doing a little contour integral around x equals 0. In practice, it's just like removing dx and setting x to 0. Then I go from having this 2 form to a 1 form, which is just dy over y times 1 minus y. And you see something very nice happened here, because now this form, which is localized on this line, now it has singularities at y equals 0 and y equals 1, and nowhere else. It has no singularities at infinity. So this is the canonical form for the interval that I see on this edge. Okay? You can similarly find that the residue here is equal to what it needs to be, and I'll leave it a little exercise for you to do the slightly more example. If you take the residue here, you also get the right answer. In other words, this notion of a canonical form has something recursive built into it. When you take the residue of a form on a facet, what you should find is a canonical form of the geometry that lives on the facet, and that you can keep on going. Okay, so you can keep on going all the way down to residues on the vertices that will be plus or minus 1. Okay, so that's what a canonical form is. It's a form that you attach to a geometry such that the only singularities are not only in codimension 1, but codimension 2, codimension 3, and you can reach all of them by taking successive residues of this form that the only singularities are on and only on the boundaries of the geometry. Okay? Now, so far we did the most trivial examples where in the end, if you just wrote down the denominators that are associated with the poles that you see, you would get everything. So I want to finish with with the two more non-trivial examples that already show you something much more interesting is going on. Let's look at this next example, which is like a quadrilateral. Okay, so let's look at the I'm going to write it like this. Imagine you have a quadrilateral, but each one of these edges is given by some linear equation. I won't write it. I'll just write it in general. Like this could be a1x plus b1y plus c1 greater than 0 is associated with this edge. Similarly, something for the other ones. Okay, so I'll call this a linear factor L1. Okay. So I similarly have an L2, L3, and an L4. And so the first thing that I could do is say that this two form should be dx dy over L1, L2, L3, L4. That's my first guess for what it could be. Okay? But this can't be the right answer. The reason is that this one certainly does have the feature. This certainly does have the feature that it has poles, logarithmic poles when L1, L2, L3, or L4 goes to 0. However, let's say that I localize myself to where, for fun, where L2 is 0. Okay, that means that I'm on this line. Right, I'm on this line. Now, on this line, there is this point, which would be where L1 also goes to 0. There's this point, which is where L3 goes to 0. Those are perfectly fine. Those are legal parts of the positive geometry. Remember, my positive geometry is inside of this quadrilateral. But there's also this point up here where L4 would go to 0. That is not in the geometry, right? This point is not in the geometry. Similarly, there is this point, which is not in the geometry. Sorry, it's a little bit far away in the way I drew it. Okay, there's this point here. So there's this point where L2 intersects L4. There's this point where L1 intersects L3. These points are not in the geometry. However, this form that I wrote down would certainly give me singularities there. You know, once I take the residue here on L1, on L2 goes to 0, let's say, then I could, after that, the next singularities could be either when L1, L3, or L4 goes to 0. Again, two of them are legal, and one of them is not. Okay? So this form cannot be the answer. However, we see what is the answer. What I need is to have a factor in the numerator which exactly kills these two residues. Okay, so I have to have a factor in the numerator. And what is that factor? It precisely has to be this line that passes through these 2 points. Okay, so there's a line whose vanishing, there's a linear equation whose vanishing determines this line that passes through these points. Let me call this L star. And so that's what the numerator has to be. The numerator has to be this interesting L star. Okay, so you see already that asking for the canonical form of a quadrilateral is making something slightly sophisticated, right? It's not a totally trivial form. It has to have this nice numerator. I'll leave you as a little exercise to figure out what happens in the case of a pentagon. And once you figure out the pentagon, you'll understand what's going on in all the cases. Okay, so I'm going to draw the pentagon like this, just to save myself some time. This is the region I'm interested in. Okay, so this is my positive geometry. So here I've drawn L1, L2, L3, L4, L5. Again, you might think that the form is dx dy over the product of the 5 L's. But again, there's a problem that some of these intersections between the L's are okay, but many of them are not. Okay, so for example, all the ones that I've drawn here, all these funny points here, all these funny points are not in the geometry, and yet this form as I've written would definitely give me singularities there. So the exercise for you to think about, going back to your high school geometry, is what kind of function should I write that puts a 0 on all of this? And the answer, I'll leave you to work it out, but the answer you might remember from high school is a conic. Okay, there's a unique conic that passes through 5 points. And so once you specify what these 5 points are, there's a unique conic that you put upstairs that kills all those singularities and which gives you this interesting canonical form. So already we see in these seemingly trivial examples of the quadrilateral, the pentagon, polygons, and the plane, the canonical form is kind of a beefy idea. It knows a lot about interesting geometry. It's not just some trivial function with a product of a bunch of things downstairs. And later we're going to talk more about different ways of getting canonical forms and ways of thinking about them. But this was just to give you an early idea of what this idea is going to be about. And already from what I told you, I hope you can see now more of what the strategy is going to be. Because we said that the amplitudes are going to be associated with canonical forms of some geometries that live in kinematic space. And since the amplitude is a canonical form, we see that the singularities of the amplitude are going to be precisely reflected in the boundary structure of these positive geometries. Okay? But we know the singularities of the amplitude are the things that are interesting. The singularities of the amplitude have to have the special features that encode locality and unitarity via factorization. The singularities of the amplitude at tree level basically tells us the singularities in some spots, and on those spots it should factor into the product of lower things. And so this feature of what the singularities look like and of the factorization is now something that has to emerge autonomously from this geometry. We should find some geometries that have facets facets in some have some nice special characterization, and such that when I go to those facets, I see that what I get is not something random. What I get is a product of lower geometries of the same class that I defined. Okay, and all of this would somehow emerge autonomously without ever saying the word Feynman diagrams and propagation and all of that stuff. But there should be some raison d'être for these geometries with these factorizing boundary properties. And that's, in fact, going to be something that we'll talk about at greater length in the rest of the lectures. Okay, so I think that's where I'll end it for today. Tomorrow we'll start with, after all this blah, blah, big picture motivation, we're going to start with a concrete example of the simplest possible theory of colored scalar particles. And we're just going to begin thinking about the kinematic space, how to label the kinematic space, and we'll follow our noses and make a few guesses, and exactly these kind of structures are going to emerge seemingly out of vapor, with a very, very few combinatorial observations made along the way. And then we'll see precisely how what I just told you works in practice, that these objects have a life of their own. They're defined by some simple ideas directly in kinematic space, but when you study them, you discover they have special boundaries that have the property that when you go to these boundaries, you get objects that factor into lower copies of themselves. And that'll be the beginning of seeing where factorization comes from, and put more meat on the bones that we just said in words today. All right, sorry for going over time. Thank you guys very much.
Let's thank Nima. So, yeah, thanks a lot, Nima. Just to let you know, tomorrow is the same time, but...
Yes,
and then,
I know. We go back an hour.
Yeah, but there's just one thing I wanted to ask. So, then there'll be a coffee break for half an hour, and then there's a discussion session. So, if you're able to... I forgot that I hadn't told you that. But so
I'll join the discussion session. That'll be great.
Yeah. Okay. So we'll do that tomorrow. Yeah. So let's break for coffee, and we'll come back in approximately half an hour. Thanks, Nima. See you tomorrow.
All right. Thanks a lot, guys. Bye-bye.